Good morning, welcome to this next lecture on complex variables. We were looking at this function which is square root of z square minus z0 square, okay, which is written as r1 r2 to the power half e to the power I theta plus phi by 2. We are looking at the second case where theta lies between 0 to 2 pi, but phi lies between minus pi and pi. So, let us examine how the function behaves, and again I mention r1 r2 to the power half is just a magnitude, so it does not bother us. So, let us see what is theta over here. Theta over here just above the x axis is 0, theta is 0, and what is phi? Phi is also 0, phi is also 0 just above the x axis. What is below? Okay, just below here, what is theta? Just below here theta now has to go full round, so theta is 2 pi. But what is phi? Phi is still 0. Okay, if I take a phasor from here and just below the x axis, okay, this angle is 0. I begin from minus pi, come around, phi is 0 here, so phi is still 0. Therefore, you see the difference now. I get e to the power 0 plus 0 by 2, which is 1. I get e to the power I twice pi plus 0 by 2, which is I pi, so minus 1. So, I have a change in sign now. I have 1 over here, minus 1 over here. Okay. For this case, e to the power I twice pi plus 0 by 2 is equal to e to the power of I pi, which is minus 1 for this lower case. Okay. So, now I have a jump in value. If I approach from top, I get 1, if I approach from bottom, I get minus 1 for this function. Let us examine in between. Okay. In between, let us say, so now my z minus z0 looks like this, and z plus z0 looks like this. So, we will have see what are the theta phi values. So, theta for this case is pi, okay, and phi for this case here is 0, okay, just as before. If we approach from below, okay, theta for this case is still pi, and phi for this case is still 0, phi is 0. So, theta pi have same values, theta phi have same values approaching from above and below. So, this function is continuous here. Let us examine what happens here. Here we have, okay, theta is equal to pi. Theta is equal to pi, and here phi is equal to pi also, okay, because why? Phi is going from minus pi, goes around once and comes back here as pi. What about below? Theta is, what is theta here? Theta here is pi, okay, theta here is pi, but phi here is minus pi, phi here is minus pi. So, above I get e to the power of I pi, here I get e to the power I0. So, the function jumps here also. So, interestingly, this region is forbidden, this region is forbidden, and this region is allowed. You can cross here, okay. So, these become the branch cuts, they go off to infinity, they go off to infinity. Okay. So, with this knowledge, let us look at a problem that involves a branch cut. Okay, the first problem involving a branch cut. So we have I given by again a real line integral 0 to infinity dx by square root of x and 1 plus x square. Okay. You can see that the integral has to go from 0 to infinity, the positive x axis. So as before, we construct another function j which will be going around a closed contour C, and we replace x with z. So we have z by square root of z into 1 plus z square. Okay. Now fairly obvious, the cut we are going to take is here. Okay. We are going to parameterize z in terms of r e to the power of I theta. Okay. And theta will be between limits 0 and twice pi. So that now for square root of z, this becomes the cut as seen before. This becomes the cut. Okay. And as I said, we need the portion to be integrated must be part of my contour. So 0 to infinity must be part of my contour. So how does that work out? Okay. So watch this. We start here just away from 0. Okay. Then we move above the cut. We move above the cut to infinity. Okay. So let this be infinity. Then I take a semicircular, I take a circular arc. This circular, okay. I go around, I come back here. Now this is a cut, so I cannot cross. So now I go along the cut till 0. Then I take an epsilon circular contour, a radius with epsilon circular contour, a circular contour with radius epsilon, and this here is r going off to infinity, and I join up. Okay. So this is a closed contour now. And my closed contour, because of square root of z, has a branch cut that goes from 0 to infinity. Okay, 0 to infinity, and I have isolated poles at z equal to plus I and z equal to minus I. Z equal to plus sign, z equal to minus sign. So now how to solve this problem? So my j is equal to integral over this closed contour C. Okay, this is my C. It is taken in the positive sense, counterclockwise sense. Okay, and I have dz over square root of z into 1 plus z square. Now I write down the individual portions. Okay. So let me call this 1, let me call this circular arc CR as 2. Okay. Then I have this portion coming from infinity back, I will call it 3. Then the C epsilon, I will call it 4. So I have 4 portions, 4 legs. So I have the integral going from 0 to infinity upper above the cut. Okay. Then I have this integral over this circular contour with radius going off to infinity. Okay. Then I have the portion that comes from infinity to 0, this portion 3, this is portion 1, this is portion 2, this is portion 3, and I have lastly this integral over C epsilon, okay, limit epsilon tending to 0. Now there are 2 isolated poles inside the contour plus minus I. So I will get residues from both, twice pi I residue, okay, from I and minus I. Okay. So immediately if you look at this CR integral using the degree of polynomial theorem, the degree of the denominator is at least 2 greater than the numerator, there is nothing in the numerator. Okay. So CR can be sent to 0 immediately, CR is 0. Okay. Now I am left with C epsilon. Let us see how C epsilon integral looks like. Okay. On C epsilon, my z is equal to epsilon e to the power of I theta. Okay. Epsilon being constant, I will move along theta. So dz is equal to epsilon I e to the power of I theta d theta. Okay. Then if we substitute this back into j, okay, I have j, no I am sorry, into C epsilon. So I have integral along C epsilon. Okay, we will put the theta limits on that in a minute. So numerator is dz, which is epsilon I e to the power of I theta d theta dz by square root of z is epsilon to the power half e to the power of I theta by 2, and then I have 1 plus epsilon square e to the power of twice I theta, and whole thing has limit epsilon tending to 0, and because of the theta definition we have, okay, 0 here, twice pi here, the theta limits on this are theta is 2 pi and theta is 0 here. Okay. Now the magnitude of this integral, the magnitude of this particular integral, okay, is less than equal to the integral of the magnitude. Okay. and limit epsilon tending to 0. We can informally see that limit epsilon tending to 0, epsilon sits separately on top. So, this will go to 0, okay. Or if we still want to do it formally, what we do is we say this is less than, strictly less than, limit epsilon tending to 0 integral theta equal to twice pi to theta equal to 0, okay. Then we replace, so we have epsilon, now I e to the power I theta go away, epsilon d theta by epsilon to the power of half, e to the power I theta magnitude is 1. Then we replace this with a smaller quantity, okay. We replace this with a smaller quantity, so that less than strictly holds, okay. So, we know those particular inequalities, which is magnitude of Z1 plus Z2 is greater than or equal to the magnitude of Z1 minus the magnitude of Z2, okay. So, here I have e to the power twice I theta, which I want to get rid of. So, what I write as 1 is the magnitude of 1 minus epsilon square. What I am saying is that magnitude of 1 plus epsilon square e to the power twice I theta is greater than or equal to the magnitude of 1, which is 1, minus the magnitude of this, which is epsilon square. Okay. So, now what happens is this is equal to the integral is equal to limit epsilon tending to 0, okay, integral. Here I will switch the integral limits because we need a positive value. This modulus we have up here is a positive value, so we have to switch the integral limits. So, I get epsilon by epsilon to the power half into 1 minus epsilon square into d theta. This quantity can be pulled out because it is not a function of theta, okay. And so, on the next page I have limit epsilon tending to 0, epsilon over epsilon to the power half 1 minus epsilon square integral with the switched limits d theta. Of course, this integral gives me twice pi, but here this epsilon to the power half cancels with epsilon and I get an epsilon to the power half, and limit epsilon tending to 0, this goes to 0. Now, what have we achieved? We have j given by this integral over the closed contour, okay, and I have the integral on the upper portion plus the integral on the lower portion plus the C epsilon contour which gave 0 plus the CR which gave 0. Okay. Now let us look at the branch cut once again. We have this upper portion, so we have a branch cut here. We have the upper portion that goes to infinity, we get into CR and CR is 0. We come back over here, then we go to the lower portion, then we close with C epsilon and C epsilon is also 0. Okay. So we now have J is equal to integral dz over z to the power half 1 plus z square in the upper part plus integral lower dz over z to the power half 1 plus z square. Now let in both these cases z be equal to r e to the power of I theta. Okay. And dz is equal to dr e to the power of I theta, because theta is a constant on each of these portions. So now J becomes equal to, okay, limit r tending to infinity integral 0 to r dz, which is dr e to the power of I theta by z to the power half, which is r to the power half e to the power of I theta by 2 into 1 plus z square, 1 plus r square e to the power twice I theta. This is the upper portion. Plus integral r to 0 dr e to the power of I theta by the same expression r to the power half e to the power of I theta by 2 1 plus r square e to the power of twice I theta. Here theta is equal to 0. Okay. This is theta 0. Theta is 0 here. And here theta is equal to twice pi. So here theta is equal to twice pi. So we get J is equal to limit r tending to infinity zero to r, theta is 0, so we get dr over r to the power half e to the power I 0 1 plus r square plus integral r to 0 here theta is 2 pi. So I get again dr divided by r to the power half e to the power of I twice pi by 2 into 1 plus r square. This gives me e to the power of I pi, which is a minus 1. And I can use this minus 1 and switch the limits on the integral. Okay, so if I do that, now integral 0 to infinity dr by r to the power half 1 plus r square plus again integral 0 to infinity dr by r to the power half into 1 plus r square. So this is essentially twice the integral I want. This is equal to 2 times I, which should be equal to twice pi I times the residue at plus n minus I. Now for the residue. Okay, the function we have is given by 1 over, the function we have is given by 1 over root z into 1 plus z square. Okay. And so we write this as 1 over z to the power half z plus I into z minus I. So the residue at plus I is given by 1 over z to the power half z plus I into z minus I multiplied by z minus I evaluated at either z equal to e to the power of I pi by 2 or z equal to I. So we get a cancellation, and for z to the power half I use z equal to e to the power I pi by 2. So I get 1 over e to the power of I pi by 4, and here I use z equal to I, so I get twice I. Okay. For the residue at minus I have z plus I divided by z to the power half into z plus I into z minus I evaluated at z is equal to e to the power of I 3 pi by 2 or z equal to minus I. Now let me explain why I have this particular expression. Okay, I have a branch cut. And on the branch cut z is written as r e to the power of I theta varying from 0 to twice pi. So theta varies, it is 0 over here, it is pi by 2 over here, it is pi over here, it is 3 pi by 2 over here, and so forth. Now when evaluating the part of the function which has given us the branch cut, we have to respect this definition so that we don't go incorrect. I have poles at plus I and minus I. So if I use minus I for this, as I am doing for this part of the function, if I say minus I to the power half, then the square root has two values. I do not know which value to choose. So it is better to use the branch cut definition. Z here is e to the power I 3 pi by 2, and z here is e to the power of I pi by 2. For the other part it does not matter, you can use z equal to I here, z equal to minus I here, but for the part that is causing the branch cut you have to respect this definition. Okay. So now this gives me 1 over e to the power I 3 pi by 4 into minus twice. So the residue contribution is equal to twice pi I into 1 over e to the power of I pi by 4 twice I plus 1 by e to the power of I 3 pi by 4 into minus twice I. Okay. Now here I will multiply the numerator and denominator by e to the power minus I pi, okay, denominator by e to the power of minus I pi, so that I get twice pi I into 1 over e to the power of I pi by 4 twice I. Now e to the power I pi gives me a negative, so I get a negative, and that negative cancels this negative. Okay. So the negative is gone, so I get a plus 1 by twice I, but this e to the power I 3 pi by 4 and minus I pi gives me e to the power minus I pi by 4, and so I have twice pi I, take twice I outside, e to the power of minus I pi by 4 plus e to the power I pi by 4. Okay. If I divide this by 2, multiply by 2, cancel twice I, I get pi into 2 cos pi by 4. This is equal to twice pi by root 2. Okay. And on the left I had twice I. 2 times I is now is equal to twice pi by root 2. And so the answer is pi by root 2. Okay. So with this I close today's lecture. Thank you.